Good morning, good afternoon, and good evening, based on when you are listening this to. My name is Ajay Salas. I'll be presenting a lightweight, delay-tolerant networking framework for resource-constrained environments. This is a work done by myself, Sharad Babu, and B.S. Manoj. We are from Indian Institute of Space Science and Technology, Thiruvananthapuram. First of all, I'll be giving an outline of the presentation. Initially, we'll be talking about delay-tolerant networks, then a solution to the delay-tolerant network, the bundle protocol, followed by our solution for resource-constrained DTNs, the lightweight DTN, the definition of bundles in LWDTN, followed by an architecture which is used in the lightweight DTN, an experimental setup and performance analysis done on LWDTN, followed by a comparison between lightweight DTN and bundle protocol, and finally the conclusions of our study. Our traditional networks are built on the assumption that there is an end-to-end connectivity from the source to the destination, but that is not always the case. In certain networks which have large delays, bandwidth restrictions, and disruptions due to intermittent connectivity, uh, this end-to-end connection is not ensured. For such networks, these networks have high error rates, and even the nodes are always mobile. And even the source and the destination need not be in the same type of network. So for such networks, commonly we call them delay tolerant networks. These networks need a proper communication protocol to communicate from one end to another. So the approach that is used for this communication is called as the bundle protocol. The bundle protocol is a non-conversational protocol which does not ensure that a connection is established between the source and the destination before it starts transmitting a message. It communicates between the source and the destination through a store, carry, and forward switching mechanism, where the data is transmitted to to a neighbor node, which stores the data and transmit to another node upon establishing another connection. This ensures that the data is transmitted from A to D. However, to ensure a reliable transmission from A to B, we need to ensure that a node accepts the custody of the data. That is, the data transmitted from A will reach node D. That is through the custody transfer approach, where the node in between takes responsibility for the data that is transmitted and stores a copy of the data. Through this, we are able to cope with intermittent connectivity, and we'll be able to take advantage of the scheduled, predicted, and opportunistic connectivity. The bundle protocol forms a part of the DTN protocol stack, where a bundle layer is added between the traditional application and transport layer. This layer gives the network the ability for store forward switching and custody transfer. It also provides the ability for the network to communicate between heterogeneous networks. For example, in this case, the second forwarding node is capable of communicating between two networks, and it acts as the bundle layer acts as a bridge between the TCP/IP network and the node TCP/IP network. Bundle protocol gives a lot of capabilities for communication in a DTN. However, it comes at a cost. The complexities in the traditional bundle protocol, which involves multiple blocks and a very high protocol overhead, is a constraint on the constrained networks. So for them with stringent resource in terms of energy, memory, and bandwidth, applying DTN over it is very costly. So there LWDTN comes as a solution. The bundles in the LWDTN are embedded only with the required attributes for communication in such resource constrained environments. We reduce the number of blocks to a single block. We also follow custody transfer approach, but it is tailored for uh, such resource constrained networks. We enable the fragmentation of packets for the maximum utilization of memory. And we do this by using three different types of bundle: data bundles, status bundles, and beacon bundles. The bundle formats in LWDTN, like I told, are divided into three. The data bundle contains the application data which is generated from the application which is using the LWDTN framework. The status bundle are used for communicating the uh, current status of data bundles which are spread across the network. Beacon bundles are used to identify or announce the presence of neighbor nodes. Then coming to the fields of a data bundle. The data bundle, um, in fact, all our bundles have a flag field in the beginning. The flags are defined by the first flag itself is the type. It defines which type of bundle it is. In data bundle, the second flag is the fragmentation flag, which shows if the bundle is a fragment. Then a not fragment flag, which ensures that the bundle is not fragmented. Then a fragmentation offset for knowing if the fragment, which fragment the bundle is a part of. A time to live field is given for knowing the exact lifetime of the bundle. A source CID and a sequence number is used for defining the individual identification of the packet. A destination EID for defining where the package is heading. The custodian EID shows which node is holding the custody of the packet. Checksum for the validation. Block length for determining the size of the payload. Port number for determining the application. Beacon bundle is a simple bundle which has a type for beacon and the node EID from which the bundle is generated. A status bundle is similar to a data bundle in terms of the header. The only difference is that the identification of the status bundle is from the source EID and the report number, and the sequence number and the source EID of the data bundle identifies which data bundle it is referring to. The flags, of course, in status bundle are different, and they define the statuses, which we'll be explaining in the next slides. So the LWDTN architecture consists of 5 elements: the application agent, a buffer, a status report generator, a bundle protocol agent, and a convergence layer adapter. The application agent communicates between the bundle layer and the application agent or the application. The buffer stores all the data that is coming across the bundle layer. The status report generator generates the statuses. Convergence layer adapter communicates with the transport layer below, and the bundle protocol agent does the heavy lifting of the bundle processing and reception. Now coming to the bundle processing, first of all, we'll go through the status report generation. Basically, we have 4 different statuses: bundle delivered, custody accepted, bundle fragmented, and bundle erroneous. These are the flags that are available in the status report. Now, the bundle delivered status is generated for notifying the entire network that a bundle has reached its destination. The custody accepted status is generated to announce to the custodian that a new node has taken custody and you can delete whatever data you're holding. The bundle fragmented status is generated to notify the nodes that only a part of the data is taken into custody and the remaining part has to be kept intact. Bundle erroneous status is generated when a checksum fails and the bundle has to be retransmitted. Now coming to bundle reception, for data bundles, the bundle can come from 2 different places. The first is from the application. That part is handled by the application agent. Now the application agent transmits the data or the bundle after adding the data bundle header directly to the buffer if a suitable link is available for communication between the or a suitable node is available for transmission. If there are no nodes available, it will transmit it to the BPA, and the BPA will give it to the convergence layer adapter, which will transmit to the nearest node. The buffer stores the data based on the availability of the link. The convergence layer adapter takes data bundles which are available in the network, which comes as a reception data. These data bundles are they also go in 2 different ways. The first way is to the bundle protocol agent, which keeps it to the buffer if it is not destined to this particular node, if it has to be forwarded to another node. If it is destined to the node, the BPA will give it to the application agent. On reception of status bundle, like I told, bundle delivered status, if you receive a bundle delivered status, it will remove the copies of the data bundle that are available with you. The custody accepted status, if it is received, the custodian deletes the bundle in its custody. The bundle fragmented status, if it is received, the fragment of the bundle that has been received by the other end is deleted. Bundle erroneous requests a retransmission and the bundle will be retransmitted. A beacon bundle on reception will update the address table in the neighbor list of the bundle. It will take the node ID from the beacon bundle and store it in the address table. The custody transfer in DTN, LWDTN is mandatory. That is, if you have space for accepting the custody, the node will accept the custody. There is no choice given to the node. And if limited space is available, custody of fragments is transmitted. Coming to the experimental test bed, which we used to verify the efficacy of LWDTN, we used a setup with the 5 different nodes, 1 stationary and 4 mobile. The mobile nodes are Raspberry Pis and laptops, and the stationary node is a desktop. We ran different network topologies throughout the experiment period, and it started from a connected network, then going into a disconnected network, and finally to a fully connected mesh. Then coming to the performance analysis, we verified 4 different parameters: the end-to-end delay in the network, the delivery ratio, buffering time, and the bundle processing time. What we experienced from this was that majority of the bundles are delivered within a short duration of time. The longer duration is taken for bundles which were transmitted during the disconnected period in the network. The bundle processing time depends on the computing power of the nodes which are holding the bundles. For example, node N3, which is having the highest bundle processing time, is the weakest node. It is a Raspberry Pi 2 module, which was the weakest among the 5 nodes. Similarly, the buffering time is indicated by the importance of the nodes in the network. For example, node N1, which was the central node, is having the most buffering time, and it was disconnected from the network for a longer period also. So the buffering time is proportional to both. We have a very good delivery ratio of almost 80% in the experiment which we conducted. Coming to the comparison of bundle protocol and the LWDTN, we have a significantly lower footprint of around 2 orders lesser than the bundle protocol and an order less than the IBR-DTN. Even though we follow a homogeneous network, our LWDTN is platform independent and can be easily ported from multiple platforms. We follow a single block operation compared to the multiple blocks available in bundle protocol and IBR-DTN. In conclusion, delays are always a part of the wireless networks that are present now and in the future. And resource constrained elements are always a part of such networks, and LWDTN comes as a solution for such resource constrained networks. We use the traditional store and forward switching mechanism with custody transfer, which is tailored for low resource environments with the capability of bundle fragmentation. We have experimentally demonstrated the efficacy of LWDTN. However, we have some more way to go. We are having we use epidemic protocol for routing. We want to replace it with an efficient routing protocol rather than the existing flooding based system. And the LWDTN does not have any security aspects which are built into it. We have to add that too, and those are our future works. And we'll be looking forward to making those, and that will be all. Thank you.